In relativity theory, time is essential. But Einstein measured time with clicks that run differently depending on the celestial body. This meant that time is regulated by the density of not just the body, but the space it occupies. Amazing, right? But he never assumed how time worked in an empty vacuum. That's space outside any celestial mapping body. Outside any celestial body, say midfield empty space far, far away from any celestial planet body. Now, how does time work? A ship does not experience time dilation, which is the slow E-ing of time matrixed with space. Einstein said time and space are physically connected. If time slows down, so does space. This is space contraction, the bending of space. But again, he never talked about light, time or space contraction, midfield, empty vacuum space far, far away. That's where time dilation does not occur. Just the opposite of relativity. So Einstein talks about tone and time dilation as if it's space. So we must assume he never talked about empty space. So why doesn't time dilation exist in space, midfield emptiness far, far away? Good question. Because in so far, far midfield, the vacuum, matter does not exist. You know, that stuff planets and stars are made of. That's the difference between relativity theory and the quantum physics theory model, where celestial affects do not exist. In fact, because of this absence of space-time, as Einstein calls it, exists far, far away. We can travel as fast as we want. The superluminal highway alignment. Imagine flying your ship so far from everything that the night doesn't just look empty. It feels empty. No planets tugging on you, no stars nearby. Just you and the dark. Here's the twist. That's exactly where Einstein's general relativity still shines. GR isn't just for places near massive objects. It's a framework for all of space-time. Curvature equals energy and momentum. The stress-energy tensor drift far enough and energy density approaches zero. The equation simplified to the vacuum case. When curvature vanishes, you land in Minkowski space, flat space-time. Out there, gravity doesn't curve your path. Gravitational time dilation disappears, not because relativity fails, but because the cause is gone. No changing gravitational potential, no slowing of clocks, but don't get comfy. Special relativity is still watching. Floor it to a huge fraction of light speed and my time slows relative to you. Kinematic time dilation, no planets required. Now the paradox, empty space acts smooth and calm in GR, yet quantum mechanics says the vacuum seethes with energy. At the tiniest scales, the Planck scale, space might be a frothing quantum foam. GR treats space-time as a smooth fabric. Many quantum ideas hint space-time could be emergent from quantum fields and information. Remove all matter and energy and maybe space itself loses its usual meaning. That's the heart of the quantum gravity problem, the bridge we still haven't built. What about a superluminal highway in the void? Tempting, but C isn't just a speed limit, it's what protects causality. Even empty space isn't truly empty. It's buzzing with 0-point fluctuations. Try to punch past light speed with mass, and the required energy blows up toward infinity. That barrier applies near a black hole or in the loneliest gulf between galaxies. Could geometry cheat the rule? In sci-fi, yes. Warp bubbles like the Alcubierre drive or shortcuts like wormholes. But current physics demands exotic negative energy densities we've never harnessed at scale. Payoff, GR rules the smooth large-scale map. Quantum theory rules the buzzing microscopic terrain. In the deepest void, clocks tick evenly unless motion messes with them. The speed of light stays the backbone of reality. If a superluminal region exists, where does standard space end and the highway begin? Is it a boundary you could cross, or would that boundary only exist when our equations finally agree?